High ground amperage in a building can stem from several sources related to nonlinear loads and grounding system characteristics. Several factors contribute to current flow through the grounding system. The first potential source is neutral to ground leakage currents. This occurs when the neutral wire isn't perfectly balanced with the hot wires, causing current to flow through the grounding system. The causes can be uneven distribution of loads on different phases, harmonic distortion creating imbalance, and insulation failures in neutral conductors. Secondly, capacitive coupling plays a role. Nonlinear loads generate harmonics that cause current to flow through the ground, especially through the capacitance between the wires and the ground. Thirdly, ground fault equipment can be a source. Faulty equipment can allow current to leak to the ground. Fourthly, nonlinear load characteristics themselves are a source. Switch mode power supplies, common in computers, faxes, and copiers, generate harmonics that can cause distortion and neutral to ground current. Fifthly, grounding system issues. An improperly bonded or sized grounding system can result in excessive ground currents. To address these issues, several solutions can be implemented. Firstly, improve load balancing. Ensure that loads are evenly distributed across all phases to minimize neutral to ground leakage. Secondly, install harmonic filters. Consider installing harmonic filters on nonlinear loads to reduce harmonic distortion and ground currents. Thirdly, check for ground faults. Use a ground fault analyzer or megger to identify and repair any faulty equipment. Fourthly, inspect grounding system. Verify that the grounding system is properly installed, bonded, and sized according to code requirements. Fifthly, increase total harmonic distortion limits. Contact the utility provider to inquire about increasing the allowable total harmonic distortion limits for the building. This may require upgrading equipment or providing additional harmonic mitigation measures. The total harmonic distortion levels on all phases indicate a significant amount of harmonic distortion in the system, which contributes to ground currents and other power quality issues. A low neutral to ground voltage suggests that the system is not properly grounded, which can lead to safety concerns and equipment damage. It is important to note that a single ground rod may not be sufficient to handle the ground currents in the building, especially with significant nonlinear loads. A larger ground grid or multiple grounding electrodes may be necessary. In the specific situation, phasor shows 6.4 amps, with a total harmonic distortion voltage of 3.7%, a total harmonic distortion amperage of 17.2%, and a crest factor of 1.55. Phase B is 93.6 amps, with a total harmonic distortion voltage of 5.2%, a total harmonic distortion amperage of 19.1%, and a crest factor of 1.45. Phase C measures 80.3 amps, with a total harmonic distortion voltage of 4.8%, a total harmonic distortion amperage of 12.8%, and a crest factor of 1.46. The neutral to ground voltage is 2 volts and the amperage on the service is 5.2 amps. Based on these readings, the high amperage on the ground conductor is likely due to a combination of factors, including the significant harmonic distortion introduced by the numerous nonlinear loads such as computers, faxes, and copiers. The uneven current distribution among the phases further exacerbates the problem. The low neutral to ground voltage at 2 volts suggests a potential issue with the grounding system's effectiveness despite the presence of a bond to the water pipe and the ground rod. This could indicate a need for a more robust grounding infrastructure. To effectively address the ground amperage issue and the associated problems with the computers, a systematic approach is recommended. Firstly, conduct a thorough inspection of the grounding system. Verify that all grounding connections are secure and properly bonded. Ensure that the size of the grounding conductors meets the requirements of the 2014 National Electrical Code, specifically referencing sections related to grounding electrode conductor sizing, such as Table 250.66. Confirm that the water pipe bond is intact and adequately sized, as it serves as a primary grounding electrode. Supplement the existing grounding system by installing additional grounding electrodes. This could involve driving more ground rods or, if soil conditions permit, installing a ground grid. Multiple grounding electrodes help to lower the overall ground impedance, providing a better path for fault currents and reducing ground potential rise. The spacing between ground rods should be at least equal to the length of the rods themselves, as per NEC recommendations. Secondly, analyze load distribution and balance. Use a power quality analyzer to monitor the current on each phase over a period of time. Identify any significant imbalances in the load distribution. Redistribute the loads as evenly as possible across the 3 phases to minimize neutral current and reduce the potential for harmonic distortion. Consider using load management techniques to further optimize the load balance. Thirdly, implement harmonic mitigation measures. Install harmonic filters at the nonlinear loads that are generating the most significant harmonic distortion. These filters help to reduce the harmonic currents flowing through the system, thereby reducing the ground current. There are several types of harmonic filters available, including passive filters, active filters, and hybrid filters. The choice of filter depends on the specific harmonic profile of the load and the desired level of mitigation. Fourthly, conduct a ground fault equipment check. Use a ground fault analyzer or megger to test each piece of equipment in the building for ground faults. A ground fault occurs when current leaks from a live conductor to the equipment grounding conductor or the chassis of the equipment. Ground faults can contribute significantly to ground current and can also pose a safety hazard. Repair or replace any equipment found to have ground faults. Fifthly, monitor neutral to ground voltage. Continuously monitor the neutral to ground voltage at various locations throughout the building. A consistently low neutral to ground voltage is desirable, but any significant increase in voltage should be investigated promptly. High neutral to ground voltage can indicate problems with the grounding system or the presence of excessive harmonic currents. Sixthly, consider a dedicated neutral conductor. In some cases, it may be necessary to install a dedicated neutral conductor for the nonlinear loads. A dedicated neutral conductor provides a separate path for the neutral current, reducing the load on the shared neutral conductor and minimizing the potential for voltage drop and harmonic distortion. Seventhly, check for loose connections. Inspect all electrical connections throughout the building, paying particular attention to connections in the panel boards, disconnect switches, and junction boxes. Loose connections can create resistance, which can lead to voltage drop, heat, and harmonic distortion. Tighten any loose connections and replace any damaged or corroded connectors. Eighthly, use shielded cables. When installing new wiring for sensitive equipment, such as computers, consider using shielded cables. Shielded cables help to reduce the amount of electromagnetic interference that can be coupled into the equipment, improving its performance and reliability. Ninthly, surge protection. Install surge protection devices at the service entrance and at individual equipment locations to protect against voltage surges and transients. Surges and transients can damage equipment and can also contribute to harmonic distortion. Tenthly, professional consultation. Consult with a qualified electrical engineer or power quality specialist to conduct a comprehensive power quality study of the building's electrical system. A power quality study can identify the root causes of the ground current problem and can provide recommendations for effective mitigation measures. The engineer can use specialized equipment to measure voltage, current, harmonic distortion, and other power quality parameters. Understanding total harmonic distortion is crucial in diagnosing electrical system issues. Total harmonic distortion is a measurement of the harmonic content present in a voltage or current waveform. Harmonics are multiples of the fundamental frequency, typically 60 Hz in the United States, and can be generated by nonlinear loads such as electronic devices, variable frequency drives, and arc welders. High levels of total harmonic distortion can cause a variety of problems, including overheating of equipment, increased energy losses, and malfunction of sensitive electronic devices. The total harmonic distortion voltage and total harmonic distortion amperage are typically expressed as a percentage of the fundamental voltage or current. A higher percentage indicates a greater level of harmonic distortion. In the provided data, the total harmonic distortion amperage values are relatively high, particularly on phases A and B, which indicates a significant amount of harmonic current flowing in the system. This harmonic current contributes to the ground current and can exacerbate power quality problems. Crest factor is another important parameter to consider. Crest factor is the ratio of the peak value of a waveform to its root mean square value. It provides an indication of the shape of the waveform and can be used to detect the presence of harmonics or other distortions. A pure sine wave has a crest factor of approximately 1.414. Crest factors higher than 1.414 indicate that the waveform is distorted and may contain harmonics. In the provided data, the crest factors are all relatively close to 1.414, which suggests that the waveforms are not severely distorted. However, even small amounts of distortion can contribute to ground current and other power quality problems. Regarding the National Electrical Code, several articles are relevant to addressing the ground current issue. Article 250 covers grounding and bonding requirements for electrical systems. It specifies the requirements for grounding electrodes, grounding electrode conductors, equipment grounding conductors, and bonding jumpers. Ensuring compliance with Article 250 is essential for maintaining a safe and effective grounding system. Article 220 covers branch circuit, feeder, and service calculations. It provides the methods for calculating the load on electrical circuits, including the demand factors that can be applied to reduce the calculated load. Accurate load calculations are essential for properly sizing conductors and overcurrent protection devices. Article 300 covers general wiring methods and materials. It specifies the requirements for installing electrical wiring, including the types of conductors that can be used, the methods for supporting conductors, and the requirements for protecting conductors from physical damage. Article 310 covers conductors for general wiring. It specifies the ampacity of conductors, which is the maximum current that a conductor can carry without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and installation conditions. Table 310.15b16 provides the ampacity of insulated conductors rated up to 2000 volts, based on an ambient temperature of 30 degrees Celsius and no more than 3 current carrying conductors in a raceway or cable. Directing factors must be applied to the ampacity of conductors when the ambient temperature is higher than 30 degrees Celsius or when there are more than 3 current carrying conductors in a raceway or cable. These directing factors are provided in Table 310.15b3. Understanding and applying these directing factors is essential for ensuring that conductors are not overloaded. Article 500 covers hazardous locations. It specifies the requirements for electrical equipment and wiring in locations where flammable gases, vapors, or dust may be present. In summary, addressing the ground amperage issue requires a multifaceted approach that includes a thorough inspection of the grounding system, load balancing, harmonic mitigation, ground fault detection, and compliance with the National Electrical Code. Consulting with a qualified electrical engineer or power quality specialist is highly recommended to ensure that the problem is effectively resolved and that the building's electrical system is operating safely and efficiently.